Howdy, we are the Powered Programmable Elbow Orthosis team, sponsored by Texas Instruments. Our team consists of David Cuevas, Nathan Glazer, Joe Loreto, and Rafael Salas.
The elbow is one of the most active joints of the human body. However, structural damage and neurological muscle disorders can impair this essential joint. Everyday tasks like drinking a glass of water become difficult. We tackled this issue with three main objectives. We hope to create a programmable elbow orthosis to provide structural support for the elbow, resist and restrict harmful ranges of motion, and assist with intended elbow movements.
The project consists of one mechanical superstructure, with 5 embedded electrical systems. The custom mechanical structure braces the afflicted joint and mounts the majority of the subsystems. The body-to-sensor interface uses a combination of angle, pressure, and electromyography sensors to encode current and intended elbow movements. Using a microcontroller, the data processing subsystem interprets the filtered signals, manipulates the information per user specifications, and translates the result into a pulse width modulated signal to be sent to the motor. The motor-to-body interface takes this signal, actuates the motors, and articulates the elbow. The power subsystem provides portable and sustained power to each component of the orthosis. The user interface allows the user to set angle limits and prompts a calibration routine.
The system includes several hardware components. It includes an orthosis structure, a motor and gearbox, a LiPo battery, a discharge protection circuit, a linear regulator circuit, a buck converter, a Bluetooth module, a DRV8848 motor driver, an MSP432 microcontroller, the ADS1299 EMG ADC, and a force-sensitive resistor.
The orthosis structure was 3D modeled and printed in acrylic. It is lightweight, easily customizable, and requires minimal machining. A future iteration can be manufactured out of aluminum to increase strength. 2-brush DC motor drives the orthosis. Each has a gearbox which uses a 950:1 gearing ratio to provide high torque while drawing low current. Also, the gearbox includes warm gears that prevent movement when the system is off, as shown in the video. Combined, the 3D printed structure and its warm geared motors create a stabilized brace for the users, which accomplishes the first objective.
An Android app allows the user to communicate with the orthosis using Bluetooth. The user sets both the upper and lower angle limits using the app slider. The transmit button then sends the angle limits to the system and prompts the user to begin EMG calibration. After calibration, the arm may only move between the user set angles, or 45 and 135 degrees in this video. Finally, on the upper right is one of the orthosis safety features, the pressure sensor. Applying uncomfortable pressure to the pad halts the system.
The orthosis system determines intended movement with EMG sensors. Gel electrodes collect electric potential differences across the biceps and triceps muscles. A bias electrode biases the user. In the following plots, the vertical axis represents muscle activity, while the horizontal axis shows time, with new signals appearing on the left. The upper two graphs plot the real-time processed signals for 2 counteracting muscle groups. The orthosis compares these 2 signals to determine motor speed and direction, as shown on the bottom graph. More active biceps muscle signals indicate intent to close the elbow, and more active triceps muscle signals indicate intent to extend it. By intercepting these myoelectric signals at the source, at the muscles themselves, the orthosis acts on less muddled and less contingent data. EMG sensors cater to users without physical strength, but with sufficient myoelectric intention. As you can see, the orthosis intercepts weakened muscle signals, discerns muscular intention, and subsequently drives the motor to help articulate elbow movement.
In conclusion, we have created a powered, programmable elbow orthosis, which supports, limits, and assists the movements of a user's elbow. Pending human testing, this project might restore upper arm functionality to users suffering from a range of injuries and disorders, namely ones which weaken muscles and muscular activity. Furthermore, its operation is not limited to the upper arm. It can be expanded to any appendage with counteracting muscle groups, like the wrist or knee. We would like to acknowledge the following people on this list for helping us achieve success during our project. That's it for our presentation, and thank you for listening.